Every day, millions of plastic cups are produced through a process called thermoforming, a precise combination of heat, pressure, and material science that turns a simple plastic sheet into a strong, functional product. Let's take a closer look at how it works, step by step, from heating and forming, to rim rolling, trimming, recycling, and packaging. The process starts with a flat plastic sheet, usually polystyrene PS, polypropylene PP, or PET. These thermoplastics are chosen because they soften when heated and harden again when cooled. The sheets are extruded, cooled, and wound into large rolls that feed into the thermoforming line. Before forming can begin, the sheet has to be heated to just the right temperature. Hot enough to allow molecular movement, but not so hot that it melts. Inside the thermoformer, infrared panels, or radiant heaters. Bring the plastic up to just below its melting temperature.
Polymer molecules that contain chlorine, oxygen, or nitrogen are called polar molecules. They have higher cohesive energies than nonpolar molecules such as polyethylene. However, because they are so large, all polymer molecules, whether polar or not, have reasonably high cohesive energies. These energies have a very important effect on many polymer properties, among them the melting point.
At this point, the polymer becomes soft and flexible, almost rubbery. Now the forming begins. The sheet is clamped in place and pulled tightly over a mold using vacuum pressure, air pressure, or both. The air is evacuated through small vacuum channels, allowing the sheet to conform exactly to the mold surface.
This is a thermoforming mold for cups, and it uses a upper mold that does the pre-stretching of the film. It's easier to see from the side how that works. Pre-stretches under the mold. So the trimming components will be in the mold as well.
Once the part is shaped, it's rapidly cooled, using chilled air or water channels built into the mold. This locks in the final geometry and restores stiffness so the cup can hold its shape. Plug assist thermoforming uses a shape tool called a plug assist to mechanically drive the heated plastic sheet into the mold before vacuum is applied. Instead of relying solely on differential pressure to pull the material into place, the plug physically preforms the sheet and forces it into a controlled deformation path. The primary engineering value of a plug assist is improved material distribution. In deep draw or high aspect ratio geometries, an unsupported sheet can overstretch, leading to thin spots and localized mechanical weakness. By engaging the plug first, we pre-stretch the material in a more uniform way. This results in tighter thickness tolerances, more predictable strain profiles, in a stronger final part. A well-designed plug can also reduce common defects, like webbing, thinning, or tearing, because the deformation is guided rather than left to chance. That often allows manufacturers to down-gauge the starting sheet thickness, since the material is being used more efficiently and less margin is required to compensate for inconsistent forming. Overall, plug assist thermoforming gives engineers greater control over the forming mechanics, enabling deeper draws, sharper features, and more consistent part quality. Anytime the geometry demands high precision or significant depth, the plug becomes a critical tool in achieving a reliable and repeatable process. The next major step is rim rolling, which gives each cup its smooth, rounded edge. First, the rim is preheated, a step called thermal conditioning. The edge is warmed to just below the polymer's glass transition temperature, TG, where the material shifts from a stiff, glassy solid to a more flexible, viscoelastic state. At this temperature, the polymer's elastic modulus drops sharply, allowing it to bend without cracking. If the rim is too cool, it becomes brittle and can develop tiny fractures called crazing. These create the white, chalky edges known as stress whitening. But if the heating is right, the polymer chains can move and realign, giving a clear, smooth, and durable rim. Once the rim reaches its ideal temperature, the cup passes through a set of rotating rollers. These rollers, made of steel or ceramic, gradually curl the edge outward and upward, while a mandrel supports the cup from the inside. The result is the familiar rounded lip that adds strength and comfort when drinking. Temperature control here is critical. Too cool and the rim cracks, too hot and it loses shape. That's why modern systems use PID-controlled heaters to keep the temperature within just a few degrees of TG. After rolling, the cup is cooled again using forced air or chilled mandrels to lock in the final shape. Each batch of cups goes through an automated quality inspection. Instead of checking every single part, machines use statistical sampling in vision systems to look for cracks, uneven curls, or surface flaws. If defects appear, the system can automatically flag or reject affected batches. Today's vision systems can catch even the smallest defects with impressive speed and precision. But there are also simpler, hands-on ways to check cup quality that don't require advanced machinery. In this test, a clear PET cup is placed in front of a uniform white background that acts as the light source. The consistent, diffuse illumination allows light to pass through the cup wall evenly. You can observe subtle changes in brightness. These variations reveal differences in wall thickness that occurred during the thermoforming process. Thinner regions appear brighter, while darker or distorted areas correspond to thicker sections or regions with localized forming stresses. By examining these patterns, engineers can quickly identify areas of non-uniform draw, residual stress, or uneven forming, all without damaging the sample. After quality verification, attention shifts to material recovery. Each thermoformed sheet leaves behind a trimmed framework, known as the skeleton, which can account for a significant portion of the original material. Rather than being discarded, these skeletons, along with any off-spec parts, are automatically conveyed to the recycling system. The collected skeletons move directly into an industrial granulator, where high-speed rotating blades cut the material into uniform PET chips. Controlling the chip size is important here. Consistent geometry ensures stable feeding, predictable melting, and proper pressure development inside the extruder. After grinding, the regrind chips are blended with our selected ratio of virgin or post-consumer PET, depending on the production requirements. This blended material is metered into the extruder's feed throat, where the process of converting solid PET into new sheet begins. Inside the extruder, the chips are conveyed by the screw through a series of temperature-controlled zones. As they advance, the material experiences both heat and shear, gradually transitioning from solid particles into a fully molten, homogenized melt. Devolatilization ports help remove any remaining moisture or trapped gases, preventing degradation and ensuring optical and mechanical consistency in the final sheet. Before the material exits the extruder, it passes through a melt filtration system that captures fines, dust, or contaminants introduced during grinding. By the time the PET reaches the die, it's a clean, stable melt, ready for precise sheet formation. At the extrusion die, the molten PET is forced through a narrow slit that defines the sheet's initial thickness and width. Immediately afterward, the sheet enters a chill roll stack, which rapidly cools and calibrates it. These rollers set the final gauge, surface finish, and overall dimensional accuracy. From there, the sheet is trimmed and rewound, ready to be fed back into the thermoforming line, closing the loop from web to chip to melt to new sheet. Once the recycled material is reprocessed into sheet stock, it's returned to the forming line, closing the loop within the production system. Meanwhile, on the main line, freshly trimmed and rim-rolled cups continue downstream. With forming and finishing complete, these cups advance to the packaging area, where they're stacked, sleeved, and prepared for shipment to customers. After trimming, the cups move into the packaging and distribution stages, the often overlooked final phase of production. Robotic stackers organize and count the cups, forming precise stacks ready for packing. These stacks are loaded into bags or cartons, which are sealed, labeled, and barcoded. Next, palletizing systems arrange the boxes into stable layers on pallets, using stretch wrap for secure transport. Automated guided vehicles or forklifts move them to staging areas for shipping. From there, products go to distribution centers, where they're sorted and shipped to retailers, restaurants, or vending suppliers. Throughout this chain, traceability data, including production date and batch information, travels with each shipment to ensure quality and accountability. From heating and forming to rim rolling, trimming, recycling, packaging, and distribution, every step in thermoforming is engineered for precision, consistency, and speed. Behind every simple plastic cup lies a complex network of thermal control, mechanical precision, and automated logistics, all working together to transform a flat polymer sheet into a reliable everyday product.
The future of plastics is one where I think plastic producers invest in municipal waste collection to get those plastics back because they see it as valuable. And ideally, they all come back for recycling, and we have, again, that circular carbon system for plastic. I also hope to see the future of plastics be one that moves away from single use and towards long-term durability. And I think that that is a trend we're already seeing start to happen. The trends of reuse, bringing your own reusable bags and silverware and cups, and also framing plastics as something that are valuable. They're not designed to be single use and disposed of in the same year they're produced. They're valuable materials that we should be keeping for long periods of time. So that's what I think the future of plastics is.
As automation and sustainability drive manufacturing forward, thermoforming shows how tradition and technology can coexist. Advances in tooling and simulation now allow engineers to predict material stretch, optimize cooling, and reduce setup time. Traditional materials like polystyrene and polypropylene remain common, but co-extruded and recycled blends are increasingly used where performance and sustainability must align. Analysts project that the global disposable cups market will reach roughly $22.14 billion by 2030, growing steadily from current levels. That forecast underlines how many millions or billions individually formed containers must roll off production lines each day, underscoring the ongoing economic weight and industrial importance of cup thermoforming. As sustainability and efficiency continue to guide modern manufacturing, the thermoforming process keeps evolving, becoming cleaner, smarter, and more circular than ever before. This is thermoforming, the art and science of shaping the future, one cup at a time.